How can PID controller wind-up issues be fixed? Imagine trying to steer a boat with a very sensitive rudder, but the rudder gets stuck or overreacts. That's similar to what happens with wind-up issues in PID controllers. When the actuator hits its physical limits, the controller keeps trying to correct, causing overshoot or sluggish responses. This can lead to unstable systems or slow recovery times, especially in robotics and advanced manufacturing. One common fix is integral clamping, also called conditional integration. This method stops the integral part from accumulating error once the actuator reaches its maximum or minimum limits. By doing this, the controller avoids building up excessive correction that can cause overshoot later. Think of it as putting a cap on how much the controller can remember errors during saturation. Another effective approach is back calculation, also known as tracking anti-wind-up. Here, the controller compares its output before hitting the limit with the actual output after saturation. The difference is fed back into the integral term, reducing it proportionally. This way, the controller dynamically adjusts its correction, preventing the integral from winding up further. It's like a smart brake that kicks in when the system is at its limit. Some controllers also reset or reduce the integral term when they detect saturation. This quick reset helps bring the system back into a normal range faster. But it's important to use resets carefully, as too many resets can cause instability or oscillations. Monitoring actuator feedback is another key. If the system detects that the actuator is at its limit, it can activate anti-wind-up logic. This process awareness helps keep the system stable and precise, especially in environments where exact control is needed, like robotic assembly lines or precision machining. Tuning the integral action conservatively is also helpful. Lowering the integral gain and increasing the time constant makes the controller less aggressive, reducing the chance of wind-up. It's a balancing act between responsiveness and stability, especially in manufacturing processes with changing dynamics. Finally, testing these strategies through simulations and real-world trials is essential. Running the system under large setpoint changes or disturbances ensures the anti-wind-up measures work well in practice. In smart factories and industry 4.0 setups, these techniques help keep robotic arms moving smoothly and manufacturing lines running efficiently. Some advanced controllers even adapt anti-wind-up parameters in real time, making the system smarter and more reliable. To sum up, fixing PID wind-up involves limiting or adjusting the integral term when the actuator hits its limits. Using methods like clamping, back calculation, and process feedback keeps the system stable and responsive. These strategies are vital for maintaining precise control in modern industrial environments.